We can determine a line in space using a point on a line. So in 3D space, this point has coordinates x0, y0, and z0, and also a direction vector, which has components v1i plus v2 in the y direction plus v3 in the z direction. So if the line passes through the point and it's parallel to the vector v, then the line is the set of all points with coordinates x, y, z, where the vector from p0 to p is parallel to the vector v, or it's a scalar multiple of the vector v. So the domain of t is from minus infinity to infinity, because the line extends indefinitely in both directions. Now if we take a position vector from the origin to point p0 and another position vector to point p, then the position vector to point p as a function of the parameter t, so this position vector can be taken to a point anywhere on the line, depending on the parameter t, is equal to r0 plus t multiplied by the vector v. So t by the vector v is this distance over here, where we're using vector addition. So we have r0 plus tv is equal to r. So in component form, this position vector has an x coordinate, and that's equal to the x coordinate of r0 plus the parameter t by the x coordinate of the vector v, and similarly the component y is y0 plus the parameter t by v2, and z is equal to z0 plus t by v3. So we're at the vector equation in component form, and the component form, where t is between minus infinity to infinity, is the standard parameterization of the line through the point p0, where the line is parallel to the vector v. So note that parameterizations are not unique, so we may use different base points or multiple powers of the parameter t, for example. So for example, if we square t, then that'll also give a parameterization of the line. Now in terms of the motion of a particle, we can rewrite the vector equation as r0 plus t, which is a time in this case, multiplied by the magnitude of the vector v, which is the instantaneous speed at time t, and we can multiply this by the vector v on the magnitude of the vector. So this normalized vector gives the direction. So essentially in this case, the line is the path of the particle. We can determine a distance from a point to a line, being the shortest distance, using the vector cross product. So if we take a vector from point P to Q, which we call PQ, and a vector V describing this line, then the magnitude of the cross product between PQ and the vector V is equal to the magnitude of PQ by the magnitude of V by the sine of the angle between the two vectors, which is this angle over here. So using trigonometry, we can see that the distance d is PQ sine theta. So therefore we can rearrange this equation to find the distance, which is the magnitude of PQ cross V on the magnitude of the vector V in the direction of the line. we can define a plane in 3D space using a point on the plane and a vector normal to the plane. So given a plane passing through this point P0 and normal to the vector n, the plane is a set of all points with coordinates x, y, z, where the vector P0 to P, which is this vector, is orthogonal to the normal vector. So in general, the normal vector is not normalized, but it's more convenient to specify the plane using a unit normal vector to avoid further calculations where we're determining the distance from a point to a plane, for example. So in other words, the dot product between the two vectors is equal to 0. So if we expand this dot product, where P0 has the coordinates x0, y0, and z0, and the normal vector can be written as a component A in the x direction, plus a component B in the y direction, plus a third component in the z direction, then the vector from P0 to P has a first component, x minus x0, and we multiply it by the first component of the normal vector. And similarly, evaluating the rest of the dot product, we have B by y minus y0 plus a third component of the normal vector by z minus z0. And that's equal to 0 by the orthogonality condition. Now this component form can be simplified further if we have A by x plus B by y plus C by z, and we take the rest of the terms to the other side of the equation. So we call this the constant d, and d is equal to ax0 plus by0 plus cz0. So you'll find these different representations of a plane in textbooks. We can determine if two planes are parallel if the normal vector of one plane is a scalar multiple of the normal vector of the other plane. So this condition states that both planes are parallel. Now if the planes are not parallel, such as in this case, then the planes intersect in a line. And we can determine a vector that's parallel to this line of intersection by taking the cross product between n1 and n2. So for example, for the case where these vectors are not normalized, they may look something like this. So they'll have the same direction as the normal vector, and n2 would be in this direction. And if we take the cross product between n1 and n2 using the right hand rule, so you'd curl your fingers from n1 to n2 and your thumb will point in this direction into the screen. So this vector v will be in the direction of the line where these planes intersect. Suppose we have a point P on a plane with the coordinates x, y, z and a normal vector n. So we'll suppose this vector is not normalized. So it may look something like this in the direction of n hat. So the distance from any point Q to the plane is the length of the projected vector, being PQ, onto the normal vector. So the projected vector will look something like this, and it's in the direction of the normal vector. So taking the dot product between PQ and a normal vector, we get the magnitude of PQ by the magnitude of n cosine theta, where theta is the angle between the two vectors, and the projection of PQ in the direction of n is PQ cosine theta. So the magnitude of this projected vector is the distance of this point to the plane. So we can rearrange this equation where PQ cosine theta is the distance d. So we get the dot product between PQ and n on the magnitude of n. And we take the absolute value in case the dot product's negative. So note that if the normal vector was specified as a unit vector, then we don't need to compute this magnitude, which will be 1. Recall that we can find the angle between two vectors using the dot product. So in this case, if we have a normal vector to the horizontal plane that's not normalized, and we take the dot product with n2, then that's equal to the magnitude of both vectors. So the magnitude of n1 by the magnitude of n2 by cosine of the angle between the two vectors. And if we divide through by these magnitudes and take the arc cosine, we get theta is the arc cosine of the dot product between n1 and n2 on the magnitude of n1 by the magnitude of n2. So the angle between the two planes is the acute angle between their normal vectors. So as you can imagine in this case, theta will be 90 degrees. Given the dot product between two orthogonal vectors is 0, and the arc cosine of 0 gives pi on 2. Find the parametric equations for the line that passes through the following points. So recall that we can define a line using a position vector, which is a function of the parameter t, and that's equal to the position vector of the initial point on the line, plus the parameter t by the vector parallel to the line, where the domain of t is from minus infinity to infinity. Well, we can choose either point as the initial point on the line, and the vector v parallel to the line can be determined from 2 points on the line being p and q. So we have a vector from p to q. So the first component is minus 4, which is minus 8 in the x direction. Minus 2, minus 5 is minus 7 in the y direction. And 1 minus 2 is negative 1 in the z direction. So given our initial point, we can write the first parametric equation of the line, which in this case will take as point P, which is 4, minus 8 by t. And the second equation is the second coordinate of the point P, plus the second component of the direction vector of the line. So that's minus 7 multiplied by t. And the parametric equation that gives the z coordinate is the third coordinate of the point plus the third component of the direction vector, which is minus t. So for t equals 0, we get point P, and we can see that when t equals 1, we get minus 4, minus 2, and 1. So that verifies our result is correct. Find the distance from some point Q to a line that's parameterized by the following equations. So we can get 2 points on the line by taking t equals 0. So that gives us a point P1, which has coordinates 0, y equals 1, and z equals 2. And the other point on the line can be obtained by choosing another value for t. So taking t equals 1, we have the coordinates of the second point being 1, 0, and 3. And from this, we can obtain the direction vector of the line, which is a vector from P1 to P2. So we have 1 minus 0 in the x direction, 0 minus 1 in the y direction, and 3 minus 2 in the z direction. So from point P1, we have a vector, and taking another vector from P1 to Q, we have 4 minus 0, which is 4 in the x direction, and 2 minus 1 is 1 in the y direction, and 3 minus 2 is 1 in the z direction. And the distance from point Q to the line is this orthogonal distance over here. So taking the magnitude of the cross product between vector P1Q and vector V, that's equal to the magnitude of P1Q by the magnitude of V sine theta, where theta is the angle between these vectors, and the magnitude of this orthogonal component is P1Q sine theta by trigonometry. So therefore we can compute the distance to the point Q as the magnitude of the cross product between P1Q and V on the magnitude of V. So computing the cross product in the numerator, we take the unit vectors in the first row, and P1Q has components of 4, 1, 1. And the vector V, being the direction vector of the line, has components 1, minus 1, and 1. So taking the determinant, we have the ith component is 1 by 1 minus 1 by negative 1, which is 2 in the x direction. And for the jth component, we have minus 4 by 1 minus 1 by 1, which is minus 3j. And the kth component can be obtained by taking 4 by minus 1, which is negative 4, minus 1 is negative 5. So we have minus 5k. So the magnitude of this vector is the square root of 2 squared plus minus 3 squared plus negative 5 squared. And the magnitude of V is the square root of 1 squared plus minus 1 squared plus 1 squared. So in the numerator, we have the square root of 38 on root 3. So the distance from the point of the line is around 3.6 units. Find the equation of the plane that passes through point P and has a normal given by the following vector. So recall the equation of the plane is the first coordinate of the normal by x minus the x coordinate of the point on the plane plus a second component of the normal by y minus the second coordinate of the point on the plane, plus the third component of the normal vector by z minus the third coordinate of the point on the plane, and that's equal to 0. So here we have 3 by x minus x naught, which is 1, minus 4 by y minus 0 plus 1 by z minus 3. And that's equal to 0. So we have 3x minus 4y plus z, and taking the other terms on the other side of the equation, we have plus 3 plus 0 plus 3, which is 6. And you can substitute the coordinates of the point on the plane into this equation. So we have 3 by 1 minus 4 by 0 plus 3, which is 6. So that's the correct equation of the plane. Find the distance from a point T to a plane which passes through 3 points, being P, Q, and R. So we need the normal to the plane to define this plane. So what we do is take a vector from P to Q and a vector from P to R, and then take their cross product to get the normal. So we have PQ is 0 minus 2 in the I direction, plus 0 minus 0 in the J direction, plus 1 minus 0 in the K direction. And the vector from P to R is 0 minus 2, which is negative 2 in the I direction, 3 minus 0, which is 3 in the J direction, and 0 minus 0 in the K direction. And the cross product between PQ and PR can be evaluated using the determinant method. So we have the unit vectors in the first row, and the components of PQ in the second row. So that's minus 2, 0, and 1. And PR has components minus 2, 3, and 0. So therefore, the I component is 0 by 0 minus 1 by 3, which is minus 3 in the I direction. And J is minus 2 by 0 minus 1 by negative 2. So we get minus positive 2, which is minus 2 in the J direction. And for the kth component, we have minus 2 by 3 minus 0 by minus 2, which is minus 6 in the K direction. So if you take the dot product between this resultant vector and these two vectors, you should get 0. So this here is the normal vector to the plane. So if we take a vector from any point on the plane to the point T, then the distance of the point to the plane can be obtained by projecting this vector onto the normal vector. So that would give the following vector, and its magnitude can be obtained by taking the dot product between PT and the normal vector, which is the magnitude of PT by the magnitude of n by the cosine of the angle between the two vectors. So we can obtain a vector PT, which is 4 minus 2 in the I direction, 7 minus 0 in the J direction, and 5 minus 0 in the K direction. And therefore the dot product between pt and n is 2 by minus 3 plus 7 by minus 2 plus 5 by minus 6, which is equal to minus 50. And the magnitude of this projected vector is the magnitude of pt cosine theta. And this is the distance from point T to the plane. So pt cosine theta is equal to d, which is thereby equal to pt dot n on the magnitude of n. And what we do is take the absolute value of the result, because distance is a scalar quantity with no direction. So what we get is the absolute value of minus 50 over the magnitude of n, which is minus 3 squared plus negative 2 squared plus negative 6 squared, which is 50 on 7.